Welcome to the last module of this course, Gaussian surfaces. This week we will be mainly dealing with the geometry of the surface. So far we have developed certain quantities related to curvature of a surface. Last time I did this theorem, Euler's theorem, and we saw that normal curvature can be realized from, so normal curvature can be expressed in terms of principal curvature. So, recall those quantities K1, K2, these are principal curvatures, and along with that I have two principal vectors T1 and T2. Now, to understand things in a little bit easy way, what I can do, whatever my surface patch is on the 3-dimensional space, maybe it is here, I can apply some rigid motion. So, I am going to write it, applying rigid motion, maybe one more, and doing reparameterization we may and will actually we will assume what, that I am looking at a point P on the surface which is 0 the origin, and that point is actually comes from the patch, it comes from the, and the patch it is sigma 0 0. We will assume the tangent plane at P is xy plane, and one more, T1 and T2 are unit vectors parallel to x axis and y axis respectively. Okay. They may not be the vector 1 0 0 or 0 1 0, but at that point the principal vectors are parallel to x, T1 is parallel to x axis and T2 is parallel to y axis. And T1 and T2 are perpendicular, that we know, if K1 not equal to K2. What we are going to show from here with this assumption, okay, first let us convince that we can do it, that is whatever the surface is, by applying some rigid motion we can always bring it back to near origin. What is our idea here is to analyze a particular point. So, I have taken a small surface patch, analyze a particular point sigma st around in terms of these vectors. So, how the surface looks like around this point P, and we will see that with this kind of assumption, any surface, any regular smooth surface you take around this P particular point which I have, which can be fixed, we can fix any point, the surface is a quadratic surface. I have not talked about quadratic surface, I plan to do it in the last lecture possibly, but anyway, so we will see what is going on. Okay. Now, So, let us start here. Since T1 and T2 are parallel to x axis and Tp is xy plane, which is of course span of sigma u at P and sigma V. So, the vector 1 0, what will happen to that? This is in the tangent plane Tp. So, it can be written as xi 1 sigma u plus eta 1 sigma v, because sigma u and sigma v span xy plane, right. So, 1 0 is a vector in the xy plane. So, it can be written in the combination of this. Similarly, 0 1, that vector also I can write as xi 2 sigma u plus some eta 2 sigma v. And let us put T I equal to xi I eta I as usual as before. Okay. Now, what happens to the particular point on the plane x y z, x y 0? Okay, x y 0 I know. Now, this is a point in the tangent plane, right. So, it can be written as x why is so? Because x y 0 can be written as, so look at a point x y, this is 1 0, x into 1 0, y into 0 1, right. But 1 0 and 0 1 I have written in this form. So, this is really the, I am in R 3. So, this is 1 0 0, right, this is 0 1 0, because x y 0 is x 1 0 0 plus y 0 1 0, and now 1 0 0 and 0 1 0 I have substituted. So, this will look like this. Okay. So, let us write it is equal to, look at the expression, I collect the term with xi and eta terms differently, I collect them. So, I write it as x xi 1 plus y xi 2 sigma u plus x eta 1 plus y eta 2 sigma v, all right. Okay. So, let it be what, some s sigma u, I call this fellow s and this fellow s and this fellow t, t sigma v. Okay. So, now this point, if I look at sigma s t, then applying Taylor's theorem, I can approximate it by around sigma 0 0, s and t is very small. So, around p. So, remember this is equal to p, right, the origin, plus s sigma u t sigma v plus some second order term, s square sigma u u plus 2 s t sigma u sigma v plus t square sigma v v v. So, this is I have written the Taylor's theorem about second term. Okay. This is by Taylor's theorem. This expression means there is some error part is there. This I am not writing equal to, I am writing it is approximately is same. If you want to write Taylor's theorem exactly, then what you should do, you should write equal to here and some plus some error term here. Okay. This is, now I write x y 0 plus this is 0, right. This fellow is 0 origin, this is my x y 0 from the previous page, x y 0 I have written it in this form S sigma u plus sigma t. So, this x y, this fellow is x y 0 plus whatever remains. Thus, if sigma s t in terms of the surface coordinates is x y z on the plane, then what is z? X, this is sigma s t dot n, because x y I have taken the tangent plane. So, the z coordinate I should get if I get sigma s t dot product with the normal, because this is, if this is the tangent plane, this is tangent plane is x y plane. So, the normal is along this coordinate. Correct, which is we know half of L square 2 m s t plus n t square, or half S t L m, this is second fundamental form comes in here. Did you understand how it follows? If I take the dot product of this fellow with n, this is in the x y plane, n is the z axis. So, dot product with n with this fellow is 0 and dot product with n with this fellow is a square, then n into sigma u u, that is our L by definition, recall L is sigma u u dot n, m is what, sigma u sigma v dot n, and what remain n, n is sigma v v dot n, correct. So, second fundamental forms comes here because only this term remains and I have just written it in a matrix form. All right. So, if I write now S t as x t 1 plus y t 2, then my z becomes half of x t 1 plus y t 2 transpose f 2, f 2 is this matrix, this is f 2, x t 1 plus y t 2. What is it by the way? Half of x t 1 transpose f 2 x t 1, t 1 transpose t 1 gives you t 1 f, what is t 1 f 2 t 1 transpose f 2 t 1, how much is that? That is precisely k 1. So, this is k 1 x square, y t 2 k 2. rest terms cross product term, if I take K1 not equal to K2, then you know T1 and T2 is 0. Okay. So, if this is assuming K1 not equal to K2, I should not have written equal to, because here I have a tilde sign approximately. So, Z is actually this one is approximately this surface. So, this is a quadratic surface, quadratic because only quadratic terms are involved. So, what it says that if I have a regular surface, then around a point it looks as a quadratic surface, and the quadratic equation of that is determined by the principal curvature K1 and K2. So, according to that we call that, so behavior of K1 and K2 determines what will this curve will look like, what will this surface looks like. So, in particular, so if I have Z is half of K1 x square plus K2 y square. So, suppose I have K1 and K2 both greater than 0 and K1 not equal to K2, then this is the equation of a ellipsoid. So, in that case this point P is called elliptical, we will call this point elliptical. If I have K1 K2 less than 0 and K1 not equal to K2, then this P is called a hyperbolic point. So, around that point P, what does it mean, why elliptical? In this case, first case around P the surface looks like a part of a ellipsoid, here the surface looks like part of a hyperboloid. Third is possibility is K1 equal to 0, that is possible, right, and K2 not equal to 0. Then what happens, P is called a parabolic cylinder, P is called parabolic. It is just K1, where is it? Yeah, K1 0, so Z looks like K2 y square. So, it is a parabolic, x moves free and y and z moves like a parabola. So, it is called parabolic cylinder. And of course, there is another possibility, K1 equal to 0, K2 equal to 0, then you know what is, P is a planar surface, Z is 0, Z looks surround P, the surface is flat. Okay. Let us see some examples of this kind of points. What happens to our most canonical examples, sphere? You know, in cylindrical coordinates this is given by cos theta, cos phi, cos theta, sin phi and sin phi and sin theta, right. You calculate E1, this will be 1, this we have done before perhaps, and G is cos square theta, L is 1, M is 0 and N is again cos square theta. K1 and K2 are roots of which matrix? You have done it, right, F2 minus k f1, which is 1 minus k 0 0 cos square theta minus k cos square theta. What are the roots? So, k 1 will be 1, that will be same as k 2, which is denoted by k. So, let us write this way. So, k 1 equal to k 2 equal to 1 and say it is equal to k. So, k is 1. In this case, what will happen? Z looks like x square plus y square, but other terms will come up, right. So, cross term will not go away here, because k 1 is not equal to k 2. What will happen to cross term? If k equal to k 1 equal to k 2, what happens to cross term, say x, say t 1 f 2 t 2, we have done it before. Similarly, t 2 f 2 t 1, we have seen, look at the proof of the Euler's theorem, a proposition before that, this is always 0. So, it will be x square plus y square. So, p will be looks like or just a sphere, it's part of a sphere, and so everywhere around of every point of p a sphere, it is looks like sphere. So, that is what the example says. Better example could be, let us take a cylinder. You calculate, and for that I give an exercise. You calculate k 1, you will have k is 0, sorry, k 1 is 1, k 2 will be 0, it does not matter. In this case, in cylinder, p is called parabolic, that was the case, right. So, cylinder around the point p, if you look at any point p, it looks like a quadratic surface paraboloid. So, any point is parabolic. Okay. To end the lecture today, I define two more quantities. So, definition. Gaussian curvature. What is Gaussian curvature? It just k g is just product of k 1 k 2, which will be k 1 k 2 are the roots of f 1 f 2 minus k f 1. So, here comes an immediate exercise that k g is actually determinant of f 2 divided by determinant of f 1, or in terms of fundamental forms it is L n minus m square E g minus f square. Second fellow is called mean curvature. Usually denoted by h. This is the average of these two, and the exercise is in terms of fundamental forms is L g minus 2 m f plus n e divided by the determinant of first fundamental 2 into first fundamental form, and k 1 is h plus h square minus k g, and k 2 is h minus h square minus k g. Solve this exercise. and remember this formula, this formulae. That is it for today. Tomorrow onwards we will talk about geodesics.